Welcome back. This video will introduce you to polygons and some attributes of them. And the remainder of the unit will focus on some special types of polygons and the various attributes associated with them as well. So first of all, what is a polygon? You probably remember from middle school talking about polygons. If you take a look at the figures on the left, those are all examples of polygons. The ones on the right are not. So now take a minute to think about what is common to the figures on the left, and what about the figures on the right makes them not polygons. So as you can see on the left here, all of these polygons are closed figures, and all of their sides are straight. And even further, their sides intersect only at the endpoints, right? Their sides are made up of line segments, and the segments intersect only at the segment endpoints. Now for the not polygon side, you see we have some open figures here, we have figures with curves on them, and then this figure over here is made up of all straight segments, but notice that the segments don't intersect only at the end points. Okay, so that makes it not a polygon over there. Formally, a polygon is a closed figure made up of 3 or more line segments that intersect only at their endpoints. Let's take this pentagon here as an example. Each segment that forms a polygon is called a side of the polygon. This pentagon has 5 sides. The common endpoint of 2 sides is called a vertex. Plural would be vertices. So as many sides as the polygon has, they have that many vertices. So a pentagon would have 5 vertices. And then finally, we can draw diagonals within a polygon, and a segment that connects any 2 non-consecutive vertices is called a diagonal. Okay, so you have one example of a diagonal here, but this pentagon actually has several others, because any segment that connects one vertex with a vertex that's not consecutive, right, non-consecutive, is considered a diagonal. So this pentagon has a diagonal here, has one here, has one here, and has one here, for a total of actually 5 diagonals here. So here's some names for some common polygons. You will have to know these names. Anything beyond 12 we generally just call by its number of sides. So a figure that has 17 sides we would call a 17gon. Some of them have some special names, and we'll see some of the special names in our studies here, but I won't expect you to memorize any of the special names beyond the ones that you see here. Anything beyond 12, we'll just name it by the number of sides. Like I said, 17gon, or something with 28 sides would be called a 28gon. So polygons can be regular or irregular. They can be equilateral or equiangular, or they could be both, right? So all of the sides that are congruent if it's an equilateral polygon, just like an equilateral triangle. We're just going to extend that understanding to any type of polygon. All of the angles are congruent in equiangular polygon. Okay, just like, again, an equiangular triangle has 3 congruent angles. So for a polygon to be regular, it must be both equilateral and equiangular. Okay, it can't be one or the other. It has to be both. It has to have all congruent sides and all congruent angles, and then we call it a regular polygon. If it's not regular, we simply call it irregular. Okay, so here on the left, you see examples of 2 regular polygons. You can see by the markings that their sides and angles are all congruent. We have a regular pentagon on the left, and we have a regular quadrilateral, which we'll, of course, come to know as a square. And then here on the right, we have some irregular polygons. Notice that this first one here is a rhombus. It's equilateral, okay, but it's not equiangular, so we can't call it regular. And then this one over here that kind of looks like an open box, like an unfolded box. It's equiangular, it has all right angles there, but it is not equilateral. And then this third one here is not either equiangular or equilateral. It's just irregular. So all three of those would be considered irregular polygons. Polygons can also be classified as concave or convex. So a concave polygon is one in which any part of its diagonal is actually outside. Okay, so let's take a look at what that means. Concave polygons means that I can draw a diagonal from one vertex to a non-consecutive vertex, and all or part of it will be outside. Take a look here. All three of these polygons have a diagonal that's actually outside of the figure, so that's considered concave. And a convex polygon has all of its diagonals inside. So these three over here on the right would be considered convex because, as you can imagine, all of their diagonals fall inside of the polygon. We deal mostly with convex polygons, but we'll see some concave ones as well. A couple of formulas you're going to have to know. Just like triangles have angle sums, there are special formulas for polygons. Okay, so to find the sum of the interior angle measures of a convex polygon, draw all possible diagonals from one vertex, creating a set of triangles. Now let's take a look at what that means. Okay. Now obviously in a triangle doesn't have any diagonals, and we know that the sum of the angles of a triangle is 180 degrees. Now let's take a look at the quadrilateral. If we choose one vertex, it doesn't matter which one, and draw all of the possible diagonals from that vertex, in this case we only have one, we can see the quadrilateral is divided into two triangles. Well, the sum of the angles of a quadrilateral is just the sum of the angles in both triangles, 180 plus 180, or 360. Likewise, in a pentagon, again, choose any vertex to start at and draw all of the diagonals from that one particular vertex. You can see a pentagon, we could split into three triangles. Okay, so we do 180 times 3 to get the sum of the angles of the pentagon, in this case 540. And finally a hexagon. If we choose one vertex, we can draw three diagonals from any one vertex. That splits the hexagon into four triangles, so the sum of the interior angle measures of a hexagon is 4 times 180, or 720. Okay, now notice that that's just the sum of the angles. None of these are actually regular polygons here. So you can't find, you would need a little more information to find the individual angle measures, but we can find the sum of all the angle measures. Unless, of course, it's a regular polygon and we know that it was equiangular. But this is just for the sum of the angle measures. That leads us to this formula. The sum of the interior angle measures of a convex polygon with n sides is n minus 2 times 180. Okay, so the number of sides minus 2, because if you remember, all of these polygons, the number of triangles is actually 2 less than the number of sides. So that's where that n minus 2 comes from. And then we multiply it by 180. That represents a single triangle. And then finally we have exterior angle sums in polygons as well. Okay, remember that an exterior angle is drawn like if you can imagine the side of a polygon extended, it would be the angle of that extended side with the other side, the adjacent side of the polygon. Okay, and you remember we did have an exterior angle theorem with a triangle where the exterior angle of any triangle is equal to the sum of the remote interior angles. Okay, well for polygons, you can notice here, on the left we have a triangle, on the right we have a pentagon. Okay, but in both cases, the sum of all those angles along the outside, all of those exterior angles, is 360 degrees. Okay, so in any convex polygon, the sum of all of the exterior angle measures is 360 degrees. Okay, so we'll spend some time tomorrow practicing with these two formulas and with some of the concepts that you learned here tonight. I'll see you in class.